Hi, in this video we are going to talk about remainder theorem and factor theorem. First, let us understand in which conditions is this theorem applicable and useful. Consider two numbers. Let's say one serves as the dividend and the other serves as the divisor. Let's say that the dividend is 40 and the divisor is 6. And you have been asked what is the remainder when you divide the dividend by the divisor, which means 40 divided by 6. Now the remainder is 4, right? The important thing is that we did not make any comment upon the quotient, right? Now, if 40 were to be divided by 5, we are going to get the remainder of 0. This is the modulus operator. So, we can make comment on whether something is a factor of another number just by looking at the remainder. The quotient is not important. In general, we use functions, that is remainder theorem and factor theorem, to make such claims. We try to find the remainder when a polynomial function is divided by another linear factor, and we make comments upon the remainder. And if the remainder comes out to be 0, we claim that x minus k is a factor, which should be which is logical, because if the remainder is 0 upon dividing a dividend by a divisor, then clearly the divisor should be considered a factor of the dividend, right? If you're unsure about what a polynomial function is, please refer to one of the previous videos in this playlist. It has been covered in quite detail over there. Now let's get to some examples of this. Let us say f of x is the function x squared plus x plus 1, and we want to divide this by x plus 1. We would have done long division if we were in grade 7th, grade 8th probably. That method is actually perfectly valid, and we can still do it over here. But long division can be time taking, and long division, since we are only interested in the remainder and not really in the quotient, we don't need to spend that much time and energy. As per remainder theorem, this remainder should simply be f of k. So first let's figure out what is k. We get information about k by comparing the linear factor with the standard x minus k. So if you compare if you equate x plus 1 and x minus k, you're going to get k is equal to minus 1. Parallelly, let's also work on another problem. G of x has been provided. We'll go into the specifics later as to what it is. And x plus 1 is again our linear factor. So comparing it with x minus k again, we are going to get k equals minus 1. Right? So as per the remainder theorem, the remainder upon dividing f of x by x plus x minus k should be equal to f of k. K in our case meaning 1, minus 1. So how much is f of minus 1? It will come out to be minus 1 whole square plus minus 1 plus 1. And this value is simply the minus 1 and 1 cancel out, and we are going to get 1. In fact, this is a special quadratic function. X square plus x plus 1 is not just any other quadratic polynomial. These are the two cube roots of unity. X cube is equal to 1 has 3 solutions, one being x is equal to 1 and the other two are complex. If you solve these two equations, just apply the quadratic formula, you're going to get the other two roots. Also, there are no real numbers that satisfy this, because if you just find out the discriminant of this quadratic expression, you're going to get minus 3, which is not a positive number, therefore there are imaginary roots. Alright, now let's see the other part. G of x is x squared plus 2x plus 1. If we compare it with the standard form of a plus b whole square, we can very easily see that g of x is indeed x plus 1 whole square. And the factor that we are trying to divide it with is x plus 1. So clearly x plus 1 is a factor of its own square. I mean, any number is a factor of its own square, right? So shouldn't we expect that the remainder when we divide g of x by x plus 1 should be 0? That is a logical argument. We test factor theorem we test factor theorem against the claim we are just making. If g of x is x plus 1 whole square and we are dividing it by x plus 1, if factor theorem is correct, then we should get that g of k should equal 0, right? And if we very quickly verify it, we will get g of k, which is equal to g of minus 1 is equal to minus 1 whole square plus 2 times minus 1 plus 1, and this value is equal to 1 minus 2 plus 1, which totally equals 0. So we have proved the validity of factor theorem over here, and this is useful. Factor theorem and remainder theorem can be used to make comments upon the remainders and factors of a given polynomial function. I hope you have learned something from this video. If there are any suggestions or comments, please feel free to post your views over here. And there are some additional material that I have provided as a practice for questions on factor and remainder theorem. Please feel free to browse through that, and thank you.